Hello everyone. I want to add a rupture disk in the safety analysis environment. First of all, I have I'm in the simulation environment and I should run and get the results. So I click on the run and get the results that is available for this simulation. As you see, we have no errors and one warning that is not important. So to protect the vessels, I'll go to the safety analysis environment, click on this part. It takes some seconds. Every vessel is locked and I cannot change any parameters of the vessels. So I click on add rupture disk, and when I'll go to the flow sheet, you can see as a plus sign that shows that I want to add in S12 stream a rupture disk. As I close to the S12 stream, you can see a blue square appeared in the stream. I click on this part and add rupture disk to the S12 stream. So as you can see, a warning yellow triangulars shows that the parameters and the definition of the parameters for the rupture disk is not completed. So I click on RT1 and go to the another window and continue to add another parameters for safety analysis environment. As you see in the equipment window, the unit operation that is protected is compressor 1. The operating temperature, I can choose from the reference part the operating temperature, and if I want to change the operating temperature, I can choose the manual from the drop-down list. But I don't change the operating temperature. In design temperature, I can choose manual and change the design temperature to 60 degrees centigrade. Also about the operating pressure and design pressure is the same as the operating temperature and design temperature. I can choose manual or different reference. I choose reference for design pressure and I choose 6 bar gauge. The yellow warning, the yellow ribbon says they create an emergency scenario, so I could go to scenarios field and create the scenario in this part. I click on this part and go to the type of the scenario, click on this drop-down list, and a window is appeared here. For this scenario, I can choose thermal expansion and the name can be changed to TE. Okay, then I click on this part and a bright yellow ribbon appears here and it says that I can open the scenario or duplicate and rename this scenario or delete this scenario. Okay, I'll go to the open scenario and click on this tab. I'll go to another window. It says that the scenario name is TE, scenario type is thermal expansion, and in this frame you can see the scenario reference stream. Also, this yellow ribbon says that a reference stream must be selected in order to calculate the relief properties. So I choose from this part S12 as the selected scenario, as a selected stream. The relieving temperature can be chosen from this drop-down list. I choose reference and also relieving pressure. When I click on this part, it says that the set pressure is equals to 6 bar gauge, and allowable overpressure for this scenario thermal expansion is 10% of set pressure, and relieving pressure is sum of these two parameters, 6.6 bar gauge. and total back pressure. As you see from this part, the total back pressure in edit part, I can click on this part. The atmospheric pressure is here, constant superimposed back pressure, variable superimposed back pressure, and build up back pressure. And total back pressure, that is some of the these parameters, that's constant superimposed back pressure, variable superimposed back pressure, and build up back pressure. I don't change these parts and click on this part and go to the another parameter that I should change. Relieving phase or method. I can choose from this drop down list the relieving phase. As you see, the relieving phase is vapor. I can choose vapor or a stream or direct integration, and or L divided by D method. I choose the direct integration method, and in this part you can see the required relieving flow. The required relieving flow according to the reference can be chosen here, or I can choose the calculated part or manual part. If I choose the manual part, change this value to required relieving flow, and if I choose the calculated, so it says that a required relieving flow is 2.5 to the power of 4 kilogram per hours. And if I choose the manual, you can see that I can change this value. So I choose the reference as the required relieving flow, and I'll go to this part. It says orifice calculation completed. They calculated RD diameter as a centimeter unit is 8.1, and the selected RD diameter can be chosen here from this part. Sizing case, if I choose the sizing case, it means that in the scenario part, thermal expansion scenario is chosen, and for calculating the selected RD diameter. For choosing from this drop down list, I can choose the 10.1 centimeter as the selected RD diameter, the calculated RD area and selected RD area, centimeter to the power of 2 are here shown here. Capacity uncertainty factor, as you see, the capacity and uncertainty factor is equal to 1, and rated capacity, that is the maximum capacity that is flowing through the valve, is 3.5 to the power of 4. And the capacity used, it means that ratio of required flow to the rated flow. As the percentage, it is 64 percentage, and discharge coefficient, it says it can be edited only at the PRD data for each phase type. The default is 0.6 and not used for the flow resistance method. It says that if I choose from this drop down list the L divided by D method for relieving phase, the discharge coefficient KD is disappeared here. So the capacity uncertainty factor, it is the rating factor due to uncertainty of flow resistance method as per API 520. It says that is the rating factor that is used to the flow resistance method, but I don't use the flow resistance method for this simulation, as this part is equal to 1. Okay, the fluid properties tab, if I go to this part, you can see the pressure, relieving pressure and relieving temperature in this window. Orifice sizing, direct integration HEM as the method that is used for orifice sizing. Type of flow is critical, and molecular weight of this S12 stream is 51.17, vapor fraction is 1, and critical flow pressure is 4.4 bar absolute. The critical flow pressure is the critical flow nozzle divided by orifice pressure is the pressure at a sonic velocity of the fluid at the nozzle or at the critical flow pressure here shows the the critical flow pressure shows the critical flow nozzle or orifice pressure, that is the pressure at sonic velocity of the fluid at the nozzle or orifice exit. And the other properties calculation is shown here. Properties calculation, pressure, temperature, mass, quality, density, and the other ones you can see from this window everything that is necessary for getting information according to your simulation. And in this part you can see the relief composition. Here we have propane and N-butane as the composition of the S12 stream. Go back to the RD1 here. I click on this part and go to the PRD data. Here in this window you can see this frame, the PRD name, calculated orifice area and selected orifice area, diameter of the orifice is here. Disk L divided by 2 is empty yet, and the statute of warning orifice calculation is completed here. In this field we can see the general parameters. The PRD type is rupture disk only. PRD name, it can be changed here, and PRD service I can change it to vapor, for example. I'm so sorry, vapor. And design code can be changed from the drop-down list according to the PD 5500 ASME 1 or other ASME section 8. I don't change the ASME section 8. And discharge to low pressure flare, no, high pressure flare. The pressure is 5 bar gauge, so I choose the low pressure flare. And in this field you can see the other parameters and values that are used in this simulation. The PRD specifics, PRD suffix, set pressure is chosen according to design pressure. If I did choose this part, I can change the set pressure by, I choose design pressure as the set pressure, and PRD knows everything that you want to add to this point, to this window, to explain about your simulation in safety analysis environment. And the other frame, pressure relief device selection, it can be selected from this part. Forward acting solid metal, forward acting scored, forward acting flat composite, forward acting domed composite, and reverse acting or graphite. Different parts, different types of the rupture disc can be chosen from this part according to your usage. And this material can be chosen here, and I don't change this part. Positive design pressure range, as you see from this part, you can choose the positive design pressure. From the drop down list we can choose the pressure or percentage. For percentage, the positive design pressure is a value that reduces the maximum marked burst pressure to determine the specified marked burst pressure. As you can see, you can go to the help and see what is the difference between the marked burst pressure and the specified marked burst pressure. So I can choose this part and change it to 0.2 bar. And negative design pressure, it says that it reduces the specified marked burst pressure to determine the minimum marked burst pressure. As you can see from the F1 help, the definition of the marked burst pressure and specified marked burst pressure, and also minimum marked burst pressure. Burst tolerance, if we choose the burst tolerance, we can increase or reduce the manufacturer's design ranges to determine the maximum or minimum burst pressure. For example, I can change it to 10%. Operating ratio can be changed here. Operating ratio also reduces the minimum burst pressure to determine the maximum allowable operating pressure. And if we want to know the definition of operating ratio, we can refer to F1 help. Okay, I don't change this part. For negative, I can change 0.1. The sizing scenario parameters, as you can see from this window, the sizing name is TE and scenario type is thermal expansion. Relieving temperature equals to the operating temperature. Relieving pressure, it is some of the valve set pressure, and allowable over pressure and total back pressure also can be some of the build-up and superimposed back pressure. The state or phase method is here. Vapor, a method that used to specify the relieving flow, is direct integration. HEM discharge coefficient is 0.6, and rupture disk L divided by 2 is empty here because we choose the HEM method as a relieving flow. Okay, I'll go to the rating tab. In this window, you can see sizing scenario name, scenario type, phase. Required flow is here, 2.5 kilogram per hour. It is required flow, not rated flow. And total orifice required and total orifice selected orifice area can be shown here. And also in this window, you can see the PRD's configuration. The set pressure increase, set pressure 6 bar gauge, and allowable overpressure, that is 10%, and relieving pressure bar gauge 6.6 bar gauge. And in this part, you can see the required split as the percentage, and the flow amount as the unit of a kilogram per hour. The flow amount is equals to required flow, 2.5 to the power of 4 kilogram per hour. Calculated RD diameter and selected RD diameter are shown here. Fraction of full lift, okay, we can it is empty here because we have vapor. If we have liquid, this section is active, but we have vapor and this section is not active. The rated flow as the kilogram per hour is 3.5 to the power of 4, and also capacity percentage. You can see the capacity percentage 154%. Okay, in this part you can see from this window the displayed rating estimates. From the drop down list, you can see the percentage orifice area as the percentage, and if I change this to orifice area used, this value is changed to the orifice area used. And if I choose the flow amount kilogram, you can see the required flow here. And if I choose from the drop down list split of total required flow, you can see these in this part 100%. And in this window and frame, you can see the emergency scenario name, type, required and calculated, required flow and calculated orifice, and PRD sizing method. It is a summary of the values that is calculated from this simulation. I can go to line sizing. Okay, in the line sizing, you can see the discharge coefficient method. It is the default method for line sizing. As you see, the PRD name is RD1. Design and rating tab can be shown here. If I choose the design as the default line sizing method is a rated area. You can see inlet and outlet flow can be chosen from this drop down list as a required flow or as the rated area or as the manual if I want to change the inlet or outlet flow. But I choose the rated area, and the inlet and outlet flow is 3.5 to the power of 4 kilogram per hour. And also required flow here is shown. And also in this frame you can see line sizing inputs, inline and outline. Rupture disc size as a centimeter unit is shown here. Nominal diameter of the pipe as inches can be chosen from the drop down list. 10.60 centimeters. Okay, you can see the nominal diameter as the inches units, because the rupture disc size as a centimeter unit is 10 centimeter. You can choose from the nominal diameter inches. If I just transform the 10 centimeter to inches, I can see that the nominal diameter of the these rupture discs can be 4 inches. And also for the outline, the nominal diameter as inches is 4 inches. And also when I choose the nominal diameter, you can see the internal diameter here. Material can be chosen here. If I choose the smooth for the pipe, the roughness as the millimeter unit is 0. And if I choose for example mild steel, you can see the roughness can be shown here as 4.5 to the power of minus 2 millimeter. And specified equivalent length, if I specify the equivalent length for the pipe length for inlet and outlet, I can change this to, for example, 2 meter for the specified equivalent length for inline, and for example 1.5 meter for outline. And also if the pipe has elevation, you can choose here, but I don't have any elevation for the pipe. And it says that for this scenario, current scenario, thermal expansion, we can run line sizing. And this yellow ribbon says for calculating piping pressure loss, you should run line sizing. Okay, I click on this part, run line sizing, and I wait until the simulation is complete. I should be patient to get the results. Okay, it says that according to section blah blah, the inlet pipe to a rupture disc during the discharge coefficient method must be less than 5/8 pipe diameters in length, and inlet pipe length is 2 meter, and 8 pipe diameters is 0.81. Okay, I should change this to 0.8, and again I run line sizing. I should be patient until I get the results. And it says that the according to the discharge coefficient method, the discharge coefficient method, it should be less than 5 pipe diameters in length, and the discharge pipe length is 1.5, and 5 pipe diameters is 1.5. Okay, I should change this 0.5, and again I should run line sizing. For the discharge coefficient method, we can see these warnings, and if we want to eliminate these warnings, it is better to choose the discharge resistance method, L divided by 10. Okay, another error, it says that inlet line pressure drop is okay, but outlet line pressure drop, calculated pressure drop 2.3 bar is higher than the specified build-up back pressure, that is 0.6. Modify your specification. Okay, the pressure drop for the build-up back pressure 0.6. I should go to the scenarios part and open this scenario and go to the scenario setup, and in this part, total back pressure, I should change the build-up back pressure to 2.2 bar or variable. Okay, I'll be back to the RD1 as the line sizing. I should run again line sizing for current scenario thermal expansion. Okay, I should wait. Okay, also it says that 2.3 is higher than the specified build-up back pressure. So again, it was I should open the scenario and build up back pressure 0.5, for example, 2.5 bar gauge, and I'll be back to the RD1, and again I'm so sorry, RD1 line sizing. The choice of the build-up back pressure was not correct because it was less than the 2.3, so I choose the 2.5 bar gauge for the build-up back pressure, and I have the precision for this simulation is too low, so I run line sizing again for current scenario thermal expansion, and I should wait for this simulation, and it takes some seconds, even some minutes. Okay, inlet line pressure there is okay, and all things for this simulation is okay. Inlet line pressure drop check, okay. Outlet line pressure drop check, okay. Okay, for this simulation I can choose the rating part, and also I can choose inlet and outlet flow according to rated or required or manual and required flow, and I can choose the edit pipes and fittings. As you see, we have the RD1 as the rupture disc, RD inlet flange here, and RD outlet flange in this part. I click on this button and add above the piping for the rating tab. I can choose from this part a fitting. For example, the type of the fitting can be chosen here. For example, I have one elbow 45 standard, and the schedule is according to standard, and nominal diameter of the flow is 4 inches, and also the other parts and material for this elbow can be chosen from here. Mild steel and roughness can be is a default for mild steel and the other parts, and the quantity of elbow is only 1. And also then after the this fitting, there's elbow, I can add and this I should choose the R inlet flange and add above a pipe. First I have elbow, then I have the pipe. For example, the standard schedule for the pipe is a standard 4 inches as the nominal diameter, and specify the material can be chosen here, mild steel, and also the length of the pipe can be chosen here, 0.7 meter. I have no elevation for this pipe, and also I can choose another, for example, add above another fitting or swedge or T according to the necessity of the simulation, I can choose fitting, and for example I can choose gate valve open. There is always open for the inlet of the RD inlet flange. The other things can be chosen from this part, and okay. And for so we have elbow 45 standard, and pipe and fitting, and for the RD outlet flange also I can add below the pipe, for example the material of the pipe in mild steel, and as you see when I choose the mild steel, the roughness as millimeter is chosen here, and the length of the pipe is 0.5 for example, and also I can choose this row and add below the fitting, for example a gate valve for the outlet of the outlet flange, that is gate valve open, and also the other values that I should choose for this part. And also I can choose this and add below pipe, and the schedule of the pipe is here, and also material can be chosen, for example smooth, roughness of smooth pipe is 0, and also the length is 0. For example 4 meter. Accept these fittings and pipes, and also I should run line sizing for current scenario according to rating tab, and I should wait some seconds or even some minutes to get the results of this simulation. A blue circle is here shown that the simulation is calculated parameters for this simulation, and I should wait some seconds. It says that inlet line pressure drop is okay, but outlet line pressure drop error. Calculated pressure drop 2.5 bar is higher than specified build-up back pressure, that is 2.5. Modify your specification. So I'll be back to the RD1 scenarios part, for example. Choose this one and open scenario, and in the total back pressure I can choose the build-up back pressure as the pressure drop in the outline 3 bar gauge. Okay, in this part RD1 and line sizing, again I run line sizing, and I should wait some seconds to have the results for these changing. It takes some seconds. Okay, I should be patient to get the required. Okay, inlet line pressure drop is okay for rating part or rating choice. And for this current scenario the simulation is complete. I can go to the scenario tab and create another scenario. For example, I can choose another scenario for this RD or rupture this as fire as a type of the scenario for the simulation fire, and change the name fire. Okay, I choose this part as the sizing case. It says that you should go to the scenario window and change the parameters according to what is necessary for scenario. Okay, I'll go to the scenario part. In this window you can see the scenario name, scenario type, and also a stream S12 as the default stream, and also relieving temperature. As you see, the scenario type is fire and relieving temperature is empty here. Relieving phase is 7.2 bar gauge and total back pressure, and also I can choose the L2D method as the relieving phase. And as you see, for this scenario, the required relieving flow can be chosen from this spot, manual or reference. If I choose the reference, it says please select rupture this diameter. If I choose the manual, also I can change this part, and if I choose the calculated, I should from the drop down list, I should change the unwetted as according to the API standard for the calculation method for fire, or supercritical. I choose the supercritical as the calculation method for this fire scenario. The wetted area can be exponent can be chosen here, and if I have the draining and firefighting, I can choose present or absent. I choose present, and a maximum wall temperature can be changed here. For example, 700 degrees centigrade. I can change this maximum wall temperature according to the reference type. As you see here, gas correction factor, also the gas correction factor can be chosen here. The gas correction factor reduces the API heat flux equation value by the gas correction factor. I can reduce the heat flux by adding the gas correction factor to, for example, 0.9. And also it says for these for vessels around the fire, we have one vessel up to 9 vessels. For example, if I have I don't have any mistake from the number of vessels, we can add 9 vessels for fire scenario. For the number of vessels here, 1 or specify combined dimension. If I have the dimension of the vessels here, I can choose yes from the drop down list, or if I don't have, I can choose no. If I choose no, the exposed area should be chosen here, and if I have the equipments and dimensions, I should choose the vessel type, head type, diameter of the vessel, and vessel tan to tan as a meter. If I have the equipment dimensions, and also elevation and maximum flame height can be chosen here. Additional area, also 50 percentage. It is the amount to add the wetted area to account for the connected piping or additional vessel geometry. Additional area, the percentage can be chosen here. Okay, I'll choose 1 yes for a specified combined dimension. The dimension for the diameter of the vessel is 2 meters for diameter, and vessel tan to tan, for example 8 meter vessel tan to tan. And also orifice calculation is completed here. As you see, the calculated area diameter as a centimeter is 3.3 centimeter, and I can choose this selected area diameter as centimeter to 3.8. okay, the other parameters you can see here, and I'll be back to the RD1 and RD1. Click on this tab. It takes some seconds. And PRD data, as you can see from this part, the PRD data, the type of the rupture disk can be chosen here. For example, according to the necessity of the simulation, and the other things, parameters can be chosen here. You see the other values in this window, and it says the selected sizing case does not correspond to the largest calculated orifice. Okay, it does. It is not so important. I'll go to the rating part, the other things can be shown here. For this scenario, fire scenario, the allowable overpressure percentage is 21. And in this part you can see two scenarios, thermal expansion and fire as the sizing case, because you have the plus line here, and the fire scenario is the sizing case for this simulation. And I'll be back to the line sizing. It's better to go to the PRE data, and as you see, scenario part, I choose the fire scenario and open the scenario. And for this relieving phase, if I choose the reference part, as you see here, it says that you can change the relieving phase. I choose the L2D method as the relieving phase. It says calculated inlet and outlet flow is less than required flow, so I should be patient to get the results for this method. And in this changing according to reference, and it says that the calculated inlet and outlet flow is less than the required flow. This is the important message for the L2D method. And I'll be back to the calculated part. If I choose the scenario, the required flow is shown here. If I choose calculated, the minimum flow, that is a flow through the valve through the RD, is shown here. And I can also vetted exposed area. I don't change this part, and I'll go back to the RD1 again. RD1 line sizing for this scenario. I choose the line sizing. It takes some seconds because, and according to the design rating for current scenario, that is fire, and discharge coefficient method that for line sizing is used, I can change this part 3 centimeter to 1 inch. Let me see. For example, 2 inches. No, it's so high. 1.5 inches for nominal diameter for this part, and for that part outline. And the material can be changed, but I don't change this part. And also it says according to section of blah blah API for blah blah, the inlet pipe to a rupture using the discharge coefficient method must be less than 5 pipe diameters. I go back to the scenarios part, and for this fire scenario, I open the scenario. I cannot change the relieving phase according to L2 divided by D for this vapor phase. And I'll be back to the RD1, and for this scenario, line sizing for this scenario. And according to, it says the inlet pipe length is 0.8, but 8 pipe diameter is 0.3, and the inlet pipe length is 0.8, so I should change to 0.299, for example. And for this part, the 5 pipe diameter in length is for discharge coefficient method 0.5, 5 pipe is 0.90. I'll change it to this part, and I run for all scenarios. These changes is for all scenarios, thermal expansion of fire, and I should be patient to get the results. It is changing the values for specified equivalent length, and the current scenario. Higher than the specified build-up back pressure, that is 0.6. I'll be back to the scenarios part and select this fire and open the scenario and select open scenario, this part, and oh, excuse me, this was the mistake that I had made for this one. Okay, total back pressure, I changed it 0.7 as the build-up back pressure, and okay, on this part. Okay, I'll be back to RD1, align sizing, and run for all scenarios, or I can choose the run line sizing for only this current scenario in this part, this specified equivalent length, everything that I want to simulate, and it says that the inlet pressure, line pressure, that is okay, and all the simulation results is okay for this line sizing. The green ribbon says okay, MPRE data. No, the rating part, I can go to the rating part. As you see, in this part I can see the emergency scenario name, thermal expansion, and the fire scenario, that the RD for is the percentage orifice area in 100%, and the flow amount used is for thermal expansion is here, shown here, and for flow amount used for RD is shown here. It says that the selected sizing case does not correspond to the larger calculated orifice. To remove this warning ribbon, I can go to the scenarios part and choose the sizing case as a thermal expansion, and the green ribbon shows that all the results of the simulation are okay. In this part you can see that the thermal expansion as a default scenario for the flow amount used is 2.54 in power of 4 kilogram per hour. Okay, simulation is over and all things is okay. Goodbye, up to the next time.